Good afternoon, everyone, and welcome to today's specialist workshop on zinc anti-corrosion coatings, hosted by the Africa desk of the International Zinc Association. I'm Shannon de Rehove from Creamer Media's Contract Publishing, and I'll be your host this afternoon. Thanks very much to our colleagues at Simena, who have once again sponsored the CPD points for this webinar, so registered professional engineers can earn excess CPD points by participating in the webinar. Today's proceedings will include presentations from 3 specialists who I will introduce as we proceed. Before we begin, please be aware that we have enabled the Q&A function, so please post your questions into the Q&A box. You'll find this on the panel at the bottom of your screen. The panelists will also answer as many of your questions as possible at the end of the presentations. We are recording this webinar and we'll be sending you the recording to you when it's available. You can interact with the panelists and other attendees via the chat box, which you'll also find at the bottom of your screen. This is an interactive workshop, so please post your questions for discussion throughout the webinar. So let's get started. Our first speaker this afternoon is Martin van Leeuwen. Martin is the Director for Technology and Market Development at the International Zinc Association. He is based in Brussels in Belgium. Martin is a chemical engineer and has wide experience with continuously galvanized manufacturing plants. He will provide a brief introduction to the IZA and will also discuss zinc anti-corrosion coatings in general. It's over to you, Martin.
Thank you, Shannon, for the kind introduction. Let me first share my screen with you so you will see my slides. Are my slides visible, Shannon?
Yes, we can see them. Thank you.
That's great. Thank you very much. Again, welcome to everybody joining this webinar. My name is Martin van Leeuwen, and as said, I'm Director of Technology and Market Development at the International Zinc Association. And today I will present to you on, give you a general introduction about zinc anti-corrosion coatings for protecting steel structures and steel products. First, a few words about the International Zinc Association. We are an industry association and we represent the zinc industry globally to sustainably grow markets and maintain the industry's license to operate through effectively managed initiatives in research and development, technology transfer, and communication of the value of zinc. That's a mouthful of words. In fact, we are a global association. We are spread over 6 continents and do have offices in North Carolina, in North America, in Brussels, in Europe. We have an office in Delhi, in India, and we have an office in Shanghai, in China. And on top of that, we have representatives in Russia, in Asia Pacific, Africa, Latin America, and other places in the world. Our association has about 36 regular members. These are mainly zinc producers or zinc producing companies. You can think of zinc mining companies, zinc smelting companies, but also zinc oxide producers, zinc semi producers, or zinc recyclers. Next to the 36 regular members, we do have 174 affiliate members. These companies are mainly first users of zinc. So you can think of zinc die casting companies, galvanizers, or other users of zinc or zinc chemicals. And last but not least, we do have 66 associate members, which are mainly other industry associations or not-for-profit research organizations. Okay, let's first have a look at the first and end users of zinc. If you look to the first use, then close to 60% of zinc is used for galvanizing, for applying zinc coatings on steel for corrosion protection. The other 40% is then split over semis manufacturing. You can think of zinc dust for zinc-rich paints. It's also used for brass. Brass is an alloy of copper and zinc, so a lot of zinc is going into brass. You can also make die-cast products from zinc itself, from zinc alloys. It's another 13% of zinc use. And the last 9% goes into oxides and chemicals. We'll hear later a presentation about metallizing, thermal spraying of zinc. The zinc wire, which is used for that process, also falls into the semis category in this slide. At the right side, it's no surprise that about half of the zinc will be used in construction products to protect steel outdoor from corrosion. Another 21% is used for transportation. Think about galvanized steel for cars. And then it goes into infrastructure, consumer products, and industrial machinery. So what is the family of zinc coatings? What kind of zinc coatings do we consider and do we have? First of all, at the left side of this picture, you see the thermal sprayed zinc coatings, or also called metallizing. These coatings are typically applied as thickest coatings in the whole range. You would find typically coating thicknesses between 100 and 250 micrometers. The thickness of the coating is flexible by the amount of passes you will have with the spraying gun on the substrate. The second category is hot-dip galvanizing. There, the coating thickness is a little bit dependent on the type of steel that you galvanize and the thickness of the steel that you galvanize, but you will find typically coating thicknesses between 60 and 100 micrometers. The third category are zinc-rich paints. Here, a paint with a high level of zinc pigments or metallic zinc dust is applied on a steel substrate. And also here you are flexible in thicknesses, but typically these paints are applied with a thickness of 60 to 80 micrometers, but we will hear much more about zinc-rich paints in a later presentation today. The fourth category is continuous galvanizing, which is used for galvanizing sheet or different kind of applications. You can find it in automotive or in white goods or in construction. And depending on the end application, you can apply a thinner or a thicker coating. The coating thicknesses typically range from 10 to 30 or 35 micrometers. And the last category here is electrogalvanizing or electroplating, which is typically used for automotive steels with a coating thickness of maximum 10 micrometers. So zinc coatings do not only provide a barrier coating, but they also provide a galvanic protection or sacrificial protection to the steel. You can see some pictures here of the various ways to apply zinc coatings. You can do it by painting of zinc-rich paint. You can do it by hot-dip galvanizing, which is the right picture, or in the bottom you see somebody with a spray gun applying thermal sprayed zinc coatings on a bridge. First of all, the barrier protection. Zinc, when it's metallic zinc, it's impermeable to all kind of aggressive materials like water, chlorides, or other kind of aggressive elements or compounds. So the zinc will keep those materials away from the steel, and the steel will not corrode and will be protected against corrosion. But also, zinc is less noble than steel. If we look to the series of electropotentials of different metals, we can see that aluminum, zinc, and magnesium are less noble than steel. So they can protect steel in a sacrificial way if they are applied on top of the steel. Zinc, again, is less noble than aluminum, so it's better to apply a zinc coating than an aluminium coating on a steel surface. Aluminium coatings hardly provide any sacrificial protection to the steel because the voltage difference of electropotentials between aluminium and steel is not large enough to give steel the cathodic protection protected against corrosion. Zinc, in this case, will work as an anode and will sacrifice itself to protect the steel. How does that work? In case you have a undamaged coating, the coating, as we have seen, can act as a barrier protection, as a barrier coating. But if the coating is compromised, if there's a holiday in the coating or a scratch or any other kind of damage, and the bare steel surface becomes visible, then the zinc starts to work as an anode. The zinc can react with water in a galvanic cell if there's water on the surface. And instead of the steel starting to oxidize, the zinc will sacrifice itself and will form zinc corrosive products like zinc hydroxide. It can fill up the scratch to give an additional protection to the steel. And it will make sure that instead of the steel showing red rust, the zinc will protect and will corrode instead. It is also depicted in this overview. At the left side, you see a schematic picture of a steel substrate, which is protected with non-zinc containing paint coatings. Once the paint is compromised and you have a corrosive environment, you can immediately see the formation of red rust in the damaged areas. But if you apply a coating which contains zinc, which can be a zinc-rich paint or thermal sprayed coating or a galvanized coating, the zinc will act as an anode and will protect the steel against this red rust formation. The atmosphere in which the steel product or construction is exposed to can vary depending on the amount of corrosivity of the environment. There's an ISO standard that classifies different C categories in terms of corrosivity, ranking from C1, which is a very mild environment, up to a C5, which is a very corrosive environment, and even a CX environment, which is an extreme corrosive environment. And if you would depict these different environments in a plot where you can see the coating thickness of the zinc versus the coating lifetime to first maintenance, you can see how long your zinc coating will last until first maintenance is required on your steel substrate. Take, for example, an 85 micrometer thick galvanizing coating in a C3 environment. You would see that the time to first maintenance will be somewhere between 21 and 42 years. Zinc is also quite durable in different chemical conditions, and the zinc corrosion is very low in a pH area of 4 until 12. That means that even in areas where the environment is a little bit acidic, like we had some kind of acidic rain in the past, zinc can still protect your steel against corrosion. And also in an alkaline environment, for example, concrete can be pretty alkaline. Steel has a protective property until a pH of 12. A few words on galvanizing, because galvanizing will not be touched upon by my two other colleagues talking later today in this seminar. So I have a few slides on that. We make the distinction between hot-dip galvanizing and continuous galvanizing. In hot-dip galvanizing, prefabricated steel parts like steel beams or steel plates or angles or strips can be dipped in a zinc bath to apply a zinc coating on top of the steel. You need to clean and prepare the steel surface first by decreasing it, removing all the oils and the dirt on top. It needs to be pickled to remove all the oxides from the steel surface. After pickling in a flux bath, you apply a flux layer, which protects the steel surface against reoxidation and increases the reactivity with the zinc in a final zinc bath, which is normally kept at the temperature of 450 degrees Celsius. Once the steel parts are dipped into the zinc, a diffusion process starts. The zinc will react with the steel will diffuse into the zinc, and the zinc will diffuse into the steel layer, and you will see that the final result is a galvanizing coating, which is a multi-metallic coating on top of the steel part. So the zinc coating has a metallic bond with the steel, therefore has a very high to the steel, and the intermetallic layers like the gamma and the delta layer can have even a higher hardness than the underlying steel itself. Therefore, these kind of coatings are very abrasive resistant, are very strong. You can smash a hammer on top of it without damaging the coating. Continuous galvanized steel is typically done on steel coils, and continuous galvanizing lines can
We seem to have lost you, Martin. I'll just give Martin a few minutes to rejoin.
Can you see my slides again?
Yes, we can see you. Thank you.
Apologies for the interruption.
No problem.
So in the continuous galvanizing process, you can see that the coil starts with decoiling, and then the sheet is first cleaned again to remove all the dirt and the materials on the surface that don't belong there. After that, the steel can go through a furnace process for furnace cleaning. But in these furnaces, you can also further anneal the steel to change or improve or modify the mechanical properties of the steel itself, like elongation and tensile strength. Once the steel has passed the annealing furnaces, it is dipped into a zinc bath. And then after the zinc bath, the coating can be annealed as well to produce galvanized coating instead of galvanized coating. And then you have a section with surface improvement. You can apply some oil on the surface to prevent the zinc from further corrosion. Or you can also apply a top coat or a paint on top of the zinc to apply in the end a duplex coating on the steel, or for example, construction products. So this process can apply different type of coatings. The well-known coating are the galvanized coatings or the zinc coatings. These are applied in thinner or in thicker coatings. The thin coatings are typically applied for automotive coatings, where for construction products you typically go with the thicker products. Then we have the galvanized coatings that are called the zinc iron alloy coatings here, where the zinc coating is run through a galvanizing section after galvanizing to let the zinc react with the iron to get a zinc iron coating. The third category are the zinc aluminum coatings, which are typically used in construction. The fourth category are zinc manganese coatings, which are both used in construction and in automotive. And the last category is an aluminium zinc coating, which with about 55% aluminium, 42% zinc, and 3% silicon. And this is a coating which is also typically used for construction. So these are the 5 typical coatings that can be applied in a continuous galvanizing process on steel sheets. And with that, I think this ends my introduction to zinc coatings. And I would like to give the word back to Shannon. Thank you very much.
Thanks so very much, Martin. I'm sure the engineers in the audience found that incredibly informative. I'm now going to hand over to Mike Taylor from PPG Protective Coatings in the UK. Mike holds an honours degree in applied chemistry from Portsmouth University. He started his career in the coatings industry in 1989 as a development chemist for Mebon Paints. He joined Sigma Coatings in 1998 as laboratory manager before moving into field technical service, supporting coating applications and customers throughout the UK. Projects he's been involved in include offshore rigs in the North Sea and numerous infrastructure projects, including the new Wembley Stadium. Mike became technical support manager for PPG Protective Coatings UK after their purchase of Sigma Coatings, and he's been technical support manager for EMEA for the last 6 years. He represents PPG Protective Coatings in technical committees in the British Coatings Federation and CEPE. Mike will discuss the use of zinc pigments in protective coatings. Over to you, Mike.
Okay, thank you very much, and good afternoon, everybody. Let me share my screen. See my screen now?
Not yet. We'll just wait a few minutes. Just let me know if you want me to share from my side. I can do that as well.
Okay, let me just try that again. Sorry about this.
There's always a technical issue, isn't there?
Yeah, sorry. Okay, so that should work now.
Yes, we can see it.
Okay, good.
Great.
Okay, so this short presentation is about the use of zinc pigments in protective coatings. And I'm going to cover composition of protective coatings and how we use zinc as a pigment, the types of coatings that the zinc is used in, and some of the application characteristics of those coatings, and some of the properties of coatings using zincs, and the standards that are related with these types of coatings and their use, and then a little bit about typical coating systems and durability. So basically, what goes into paint? Paint's fairly basic in its makeup. Most paints consist of 4 main ingredients: binders, the pigments, solvents, and the additives. The additives themselves, they're usually used in low amounts, and they're used to decrease foam, stop the coatings bubbling, maybe aid the flow of the coating, or add thickener to the coating. The binder is the main ingredient, and that's generically how paints are usually named. So you'll hear epoxy coatings, silicate coatings, polyurethanes, acrylics, alkyds. Those are probably all sorts of types of coatings that you've heard about. They're usually liquids, and the other ingredients are mixed into them. It's not a great scientific process in terms of mixing. If you imagine a food mixer at home, most paints are made in basically big food mixers, a blade spinning at high speed. The pigments are added to the resin, and then some solvents, and it all blends together. That's mainly how most paints are made. So you could actually make some at home if you wanted to. The resins themselves, they give the main properties of coatings. There could be 2-pack coatings like epoxies, or you might have your single-pack coatings like your alkyds. Another main ingredient is the solvents. So they enable the application, they also enable us to make the paint as well, because obviously you have to add some solvent to get the right viscosity for the coatings to be mixed. They affect the drying and curing of the coatings. And there's different types of solvents, from the aliphatics, the aromatics, alcohols, ketones, and now we're seeing more in the way of water being used as a solvent or diluent for coatings. The solvents themselves, it's very important that you use the correct solvent in your coatings, because they can react with the resins, and then you get different compositions that you don't really want in the coating and get adverse reactions. And the third main ingredient is, of course, the pigments. This presentation today is mainly around the zinc dust, which is used as an anti-corrosive pigment. But there's also other anti-corrosive pigments as well. Most common is zinc phosphate. That's used as anti-corrosive. In the good old days, we used to have lead and zinc chromates, very effective anti-corrosive pigments, but now they've been phased out, quite rightly, for health and safety. They're not the nicest pigments to work with. In terms of other pigments that we use, there's coloured pigments like titanium dioxide, the most used pigment in the coating industry in terms of colour. Red oxides, so red iron oxide, yellow oxide, carbon black. Some of these are organic pigments, some of them are inorganic pigments. Organic pigments tend not to have the same colour durability as inorganic pigments, but the inorganic ones tend to be a bit more expensive. Other types of pigments we use are barrier pigments, so aluminium flake or MIO, micaceous iron oxide. These pigments are flatter in their shape and act more as a barrier to decrease water permeability through the coating. And the final type of pigments are what we call fillers. So these are usually dug from the ground: china clay, talc, barytes, barium sulfate. They tend to just give us extra volume solids into the coating, but they're fairly inert. They don't have any particular other reason to be in the coating other than that. So moving on specifically to zinc as a pigment. Zinc is used in its powder or dust form. It's grey in colour. It's used as the anti-corrosive pigment, and it's designed to protect the steel structures, usually in construction and marine applications. There's 2 main types of coatings that use zinc. These are primers based on silicates and also primers based on epoxy. And if we look at those 2 in a little bit more detail. So zinc silicate coatings are inorganic coatings, which is a little bit unusual in the coatings industries. Most of the coatings are based on organic resins, but zinc silicates are inorganic. They're typically supplied as a liquid binder, so you tend to get a plastic bottle of liquid and then a zinc powder, and you have to mix them prior to application. In terms of drying and curing mechanism, the solvent evaporation is the first way that the coating starts to dry, and then the ethyl silicate reacts with water to form I don't know quite how to pronounce it, but silanol and ethanol, and then the molecules cross-link to form a silicate polymer. And the zinc.
Mike,
Yes, sorry.
I'm sorry to interrupt you. We seem to be having a bit of a problem with your sound. I'm not sure if maybe your speaker's not plugged in correctly.
As far as I know, it's okay.
It seems to come in and out.
Oh, sorry about that.
No problem.
I don't have another microphone, so shall we try to carry on and see how we go?
That sounds fine now. Yes, thank you.
Okay. Drying and curing mechanism, and you have the solvent evaporation first, and then the ethyl silicate reacts with water to form silanol and ethanol, and then the molecules cross-link to form a silicate polymer. And the zinc ions actually also catalyze the reaction as well. There are water-based zinc silicates as well, but this presentation mainly concentrates on the solvent-based ones. The film is a silicate matrix, and the zinc particles and the zinc dust are encapsulated into that matrix. And the zinc, as Martin mentioned, provides galvanic protection to the steel. With also, when you do get corrosion, some of the corrosion products are also insoluble, and they further protect by acting as a barrier. As Martin mentioned, the galvanic process only starts to occur once you have some damage through the coating to the steel. Before that, it does act as a barrier coating. Properties of the zinc silicate film. It's a very tough abrasion resistant film. It actually can be used also for slip resistant coatings and bolted connections. There's a couple of standards that are tested there. That's the ASTM A490 and the EN 1090 Part 2. So basically on the slip resistant, on the slip coating bolted areas, they only apply the zinc silicate. There's no other coating, and then the two zinc silicate faces are put together. So you get your corrosion resistant, but you also get this slip resistance as well. So the bolts shouldn't move when the construction is in place. Zinc silicates give excellent corrosion protection, but they also give high temperature resistance as well, up to about 400 degrees if it's just a zinc silicate coating on its own, or you can top coat them with something like a silicone, and you'll get up to 540 degrees. So you can imagine if you use it on the outside of a chimney, for example, you could use the zinc silicate and then overcoat with a silicone in a particular colour. We see quite a few of the red, white chimneys in around. That's typically what this could be used as that system. The silicates also have very good chemical resistance, especially to solvents. Martin mentioned that you have to watch the pH range between 4 and 12. Outside that range, you can get a reaction with the zinc. But for tank lining, for example, you could use a zinc silicate coating at typically about 75 microns dry film thickness, and it's very good for resistant to solvents, even for aggressive chemicals such as methanol. One thing with zinc silicates is they can be tricky to overcoat, and I've got a few comments on that later on in the presentation. Another area where zinc silicates are used is as prefabrication primers. They're also known as shot primers or weldable primers. These are typically applied on an automatic line, as shown in the picture alongside. Typically thin film applications, 18 to 25 microns, and you can weld through that coating without affecting the weld strength or any of the properties of the weld. The zinc level in this is usually lower than in standard zinc silicates. Usually around about, well, up to about 40% zinc by weight in the dry film. The reason for that is that if you put too much zinc in, it can affect the weld, but also because of the zinc fumes that are given off during the welding process. All the prefabrication primers, shot primers, etc., would be tested for health certificates as well before they're used in this way. If you just have a prefabrication primer on at about 18 to 25 microns, typical durability, depending on the environment for that type of coating, will be around 6 to 12 months. But you would need to do some secondary pre-treatment prior to overcoating it. The idea of the prefabrication primer, of course, is just to protect the steel until it's welded into place on a structure. So for a tank, say a storage tank, for example, they produce the plates, take them to site, weld the plates together, to produce the tank, and then they would put the longer term overcoated system on top of the prefabrication primer. So the other type of zinc primers that are typically used would be the zinc epoxies. The zinc epoxies differ from the zinc silicates in that they're an organic coating, and they typically consist of a two-part product. So you've got your base component into which the zinc powder is mixed, and then an amine is usually used as a hardening, maybe an amine as well, but typically an amine. and the two are mixed together prior to application. The curing mechanism for that again is solvent evaporation and then reaction between the epoxy and amine reactive groups to give a cross-linked film. And in this case, they don't require moisture to cure. In terms of properties of the zinc epoxy, again, a tough film. You can have slip resistance certification with these, but usually the zinc silicates are used. Good corrosion resistance when they're used as part of a coating system. They are easier to apply and repair than zinc silicates, but they're not as chemical resistant. When you're coating with zinc coating, it's also important to note that if you leave a time between the zinc coating being applied and the intermediate or top coat being applied, they can be subject to contamination with zinc salts, and it's important that these are removed before you overcoat them. Zinc epoxies can also be used to spot repair galvanized steel if that's broken down, for example. Protection using zinc, Martin went through this beforehand, but initially the coatings act as a barrier, and then if the coating is damaged down to bare steel, then the zinc will give some sacrificial protection. And some of the corrosion products can also act as a further barrier. Zinc pigmented primers generally offer better corrosion creep resistance than non-zinc primers. So the creep resistance is, as demonstrated in the photograph, where you have a damage to the coating film down to the steel. There's a tendency for the corrosion to spread from that damage underneath the coating film. Zinc pigmented primers are far more efficient at preventing that spread, so the damage is usually limited until you have a chance to repair it. When the test in the ISO 12944 testing, actually, that's one of the key parameters. It's the spread of the zinc. The limit to pass the test is 3 millimeters spread from the scribe in the tested panel. And the actual cyclic testing is quite a tough test. It consists of days one. It's a 7-day test. Days 1 to 3 are a UV condensation cycle, followed by 3 days of neutral salt spray, and then 1 day of low temperature. And then that cycle is repeated depending on the test that you're doing, either to C5 or CX. There's a cycle of either 16 or 25 cycles. In terms of preparation of the steel substrate for applying zinc coatings, it's very important that the zinc pigments has direct contact with the steel substrate. You have to have that electrical contact between the two metals. And the minimum recommended steel preparation is to abrasive blast clean to achieve SA 2.5 standard of cleanliness. And typically the profile would be 50 to 75 microns. It's not because of the way that you want the zinc to work in terms of electrical contact between that and the steel. There's no point in putting a zinc-rich coating over the top of another non-zinc coating because obviously you're breaking the contact. Application of the coatings. Zinc silicates generally have to be applied by spray application. They can be tricky to apply. It's very important that the coating is, once you've mixed the binder and the zinc dust together, that you continue to mix the coating when you apply it, mainly because the zinc powders are very dense and it settles to the bottom, so you need to keep it in suspension. You should apply zinc silicate as a visibly wet film. It's quite easy to get it to dry, to what we call dry spray. That's where basically the coating dries in the spray fan before it hits the object that you're coating, so it arrives on the surface as a powder with no cohesiveness to it at all, and you usually brush it off with your hand. You notice on your hand a grey dust, so it's important you get a visible wet film. Zinc silicates do require some moisture cure, so the relative humidity should be above 50%. If you try to cure them below the 50% humidity, it takes an exceptional long time. In fact, with zinc silicates is one of the only coatings that I can advise you that if you're finding the cure is a bit slow, to actually pour some water on top of it. It won't affect the coating once it's dried, but it will accelerate the cure. The film thickness should also be controlled to avoid something called mud cracking, which I'll show in the next slide. But if you imagine the bottom of a riverbed that's dried out, This is when you over apply the coating. It's typically the dry film thickness for zinc silicates between 50 to 75 microns recommended. If you get up to 100 microns and above, you can find you can get this mud cracking into it that occurs. And the cure should be checked prior to overcoating. This is done with the ASTM D4752 MEK, methyl ethyl ketone rub test. It's basically you put the solvent onto a rag and you do 50 double rubs and check whether how much of the rag is discoloured by the zinc coating. It's important to do it before you overcoat it, because obviously once you put a top coat over the zinc silicate, it's no longer going to have the humidity to keep the cure to go to completion. Another issue with zinc silicates is, as the silicate coating is porous, you can get pinholing of the top coat, so you need to use a sealer coat. You can either use independent single sealer coat, usually thinned down quite a lot, so that the solvent drives the air out of the porosity of the zinc silicate, or you can use what we call mist coat full coat technique, where you use your main intermediate coat with a very thin film to start with, and then complete the coating with a full film. And just to show you what pinholing looks like, on the left hand side of the screen, you can see the little bubbles. You don't tend to see these in the silicate itself, and you may not see them in the intermediate, but where you'll definitely see them is if you put a glossy top coat on. They're hard to repair, and once you've got an area like this, really you need to go right back to the silicate to repair them. And on the right hand side of the screen, you'll see what you can get the mud cracking if you over apply zinc silicate to higher film thickness. Zinc epoxy coatings tend to be a bit easier to apply. That's one of their advantages. Again, usually by spray. You can apply them by brush. You have to make sure you mix the base and hardener at the right ratio and use the right thinners. The control of the film thickness, you have to control it, but it's not usually quite as critical as with zinc silicates. You can apply slightly higher film build and get away with it, shall we say. But bear in mind that these zinc coatings are highly pigmented and not cohesively as strong as some other coatings. So if you apply then a very high build epoxy coating over a zinc coating, you can find the stress as the epoxy coating cures can break cohesively within the film of the zinc coating. So that's another good reason to keep the coating application tightly controlled. In terms of standards relating to protective coatings and zinc coatings, the main standards we use for specifying protective coating systems are the ISO 12944 and the NORSOC N501. The NORSOC N501 relates to offshore structures. The ISO 12944 relates to onshore and, in the new edition, offshore as well, basically incorporating the ISO 2340 that was used in the NORSOC N501. The other standard you might come across with zinc coatings is the SSPC Paint 20. In the SSC Paint 20, it specifies the amount of zinc weight in the dried films. It's got 3 levels. As you can see there, level 1 greater than 85%, level 2 77 to 85, and level 3 65 to 77%. The ISO 12944 specifies a zinc rich, or clarifies a zinc rich coating as something with greater than 80% zinc, as does the NORSOC N501. And that's where the vast majority of zinc coatings are in level 2 to the SSPC. There was a discussion of whether you need more than 85% to get good corrosion protection, but generally we find that coatings that contain even lower amounts of zinc than even level 3 can still give you very good corrosion protection, and in some ways better than non-zinc coatings. Where would you use the zinc coatings then? So the classification of environments according to ISO 12944 Part 2. The environment categories in the left-hand column are rated from C1 to CX, and with a description on the right-hand side of what those environments would be. The way the environments are actually judged is how much thickness loss of steel would be on the plate that's left in those environments for a year. So you can see on the thickness loss there, the micron relating to each category of the environment. But if you did a description of the environments, I would suggest that zinc rich primers are generally used in the C5, CX and C4 environments. For C3 and C2, they're not generally needed. You can still get a very good durability without using zinc. It's the harsher environments where zinc coatings really come into their own. In terms of durability, the ISO 12944 Part 1 lists 4 durability levels now. Low durability is up to 7 years, medium 7 to 15, high 15 to 25, and very high durability is greater than 25 years. And they suggest that durability is the time from coating up to when major maintenance is required. They use the ISO RI3 corrosion scale to give that limit. So when 10% of the area has reached RI3, it's considered that you would need to do major maintenance. Durability is not the same as guarantee. Typically, a guarantee for a 25-year durable system, you could possibly look at 10 years, certainly 5 years guarantee, possibly 10, possibly 15. It depends, but that would be judged by the manufacturer of the coating and the other parameters as well, commercial parameters as well, probably. Excuse me. So what about typical systems? As I mentioned before, the typical dry film thickness for a zinc primer is 50 to 75 microns. And for a very high durable system, so greater than 25 years, a typical dry film thickness, total dry film thickness, this is the whole system. The various environments are listed there. So for C3, you'd be looking at 200 microns of a coating system, C4 260, and C5 320. And for CX, which doesn't have a very high durability category, CX systems are considered to be highly durable rather than very high durable. So we can't give you a CX very high durable system, but the total dry film thickness there is 280 microns. And this is using a zinc-rich primer. If you use a zinc phosphate primer, then typically you'd be looking at dry film thickness of an additional 40 to 50 microns for each of these categories. So a typical coating system for a marine environment with very high durability. So this wouldn't be offshore. This picture's a little bit misleading, but this would be a coastal environment, for example, for the zinc silicate. Will be shown there. So a total of 320 microns. I mentioned there about the epoxy sealer there to prevent the pinholing of the coating system. You could use it as the one coat of sealer, or you could use it as a mist coat using the epoxy intermediate at 210 microns as a mist coat, full coat technique. With the zinc epoxy primer, you don't need a sealer coat. You can just apply the intermediate coat directly onto the zinc epoxy primer. And as I mentioned before, noting that equivalent non-zinc systems would be approximately 40 microns higher to get the same durability. So that was a quick overview about zinc as an important anti-corrosive pigment for coatings, typically used in silicates and epoxies. Zinc silicates can also be used in high temperature areas. The advantage of the epoxies is generally they're easier to apply and maintain than zinc silicates, but they both give excellent corrosion protection when used in suitable systems. So thank you for your time. I hope that was interesting and provided you with some information.
Thank you so much, Mike, for that very informative presentation on zinc coatings. I'm just going to quickly stop sharing your screen. There we are. And now I am going to pass over to Ian Blacklock. Just before I do that, though, I'd just like to remind the audience that if you want to send us any questions, please do so and send them to the Q&A box. Now, our final guest, as I said, is Ian Blacklock from Metallisation UK. Ian is one of Metallisation UK's export regional sales managers, offering sales and technical support. With his positive and friendly way of working, Ian works closely with his clients to achieve their goals. He has worked for Metallisation since 2008 and has a passion for thermal spray coatings and the wide range of applications where they can be used, including for long-term corrosion protection, decorative and engineering applications. Ian will take a detailed look at the inside track on zinc thermal spray. Also, just a note to let you know that Ian is unfortunately suffering from a voice problem. So if he does have to, he's going to pass his presentation over to his colleague, Jay Ackerman, who is the sales director, to continue if it's necessary. So in the meantime, I'll pass over to you, Ian.
Good afternoon, everyone. If there is intermittent sound, it's not my microphone like Mike's. It is my voice. So if I do need to bail out, Jay is on standby just to take over the presentation. So okay, I'll just get this going. Is that sharing okay?
Yes, it does appear to be sharing.
Is it as the full screen as well, please, Shannon?
It's not yet as full screen. We'll just give it a few seconds, but it should work. I think maybe if you change it at the bottom of the screen, it should show.
Again, it worked so smoothly before.
Of course.
Just bear with me. Sorry about this, guys.
No problem. It's the nature of technical things, isn't it?
Let me just stop sharing and I'll start it again.
Okay.
Okay. Is that
Great.
better?
Yes.
Yeah, okay, perfect. Sorry about that, guys. Okay, my name's Ian Blacklock. I'm a regional sales manager for Metallisation. I cover UK territory as well as various global territories for Metallisation. Today, going to be doing a presentation on thermal spray zinc, or TSZ, of steel, and concentrating on basically how these coatings are applied. Just a little bit of information about Metallisation. First of all, we're coming up to our centenary year next year. We're an independent business and we're the only UK manufacturer of thermal spray equipment. 45 employees, turnover in the region of 14 million. We supply the system, manufacture and supply the systems as well as a wide range of consumables. And the key to our success as a company is we're small enough to care, but we're large enough to deliver as we're a global market leader. So the big question is, what's thermal spray zinc? Martin's already touched on the differences between thermal spray, galvanizing, paint. So we're just going to go into a little bit more detail of that and some of its applications. So thermal spray zinc, it's a method of corrosion control. So we're looking at the protective coatings. The coating itself is metallic, 100% metallic, and it's a sprayed coating. So it's a zinc metallic and it's sprayed rather than zinc and hot tip galvanized. History of the process, it's not known by many, but it's actually a very old process dating back to the start of the 1900s. Dr. Shoup was the pioneer of the process, finding that pouring molten metal into a high pressure gas stream created molten particles. These were propelled onto a surface which built up a film thickness, which gave you the coating and gave you the protection. So Metallisation started in 1922, which was our foundation year. The basics of the process, you've got a feedstock, so that's either powder or a wire. Most of what we're talking about, or all of what we're talking about today, will be the wire. We have a heat source, whether that's an electrical or a flame heat source. We use that to melt the wire. We create molten particles, very small molten particles, and these are propelled onto a prepared surface, which the molten particle will then splat, cool and shrink instantly, and it will build up a coating. So you build up a coating with the number of passes that you basically use. So some highlights of the process. It's instant curing. There's no drying time. There's no curing time. It's not like paint. As soon as it's sprayed, it's cured. You'll never touch it wet or molten. It's a metallurgically cold process. So unlike galvanizing, you get virtually no heat input into the substrate. So you wouldn't expect to see more than 80 degrees centigrade heat increase on the steel, and this can be controlled by the techniques that you use for applying the coatings. It's typically mechanically bonding process. There are a couple of exceptions. Normally the preparation is grit blasting rather than bead blasting. We'll go into that in a bit more detail. But sometimes for other applications there's machining or preheat, but we'll be concentrating on grit blasting today. You can spray a range of different materials with the process. Today we're talking about zinc, but other materials can be sprayed with the systems. And it can be applied at various thicknesses. So typically 100, 150 microns minimum, up to 350, but there are applications with thinner film and there are applications with thicker film thicknesses as well. It gives very long life corrosion protection, so 20 years plus to first maintenance in a splash zone. And it's a line of sight process. There's various reference standards for the process, for the application, specification of coatings, and so on. There's company's own standards, there's NORSOC, so there's a lot of details to make sure that you do this correctly and assistance in doing so. So let's look at a couple of typical applications of the process. So here's just a few. So we've got bridges and infrastructure. So whether that's zinc coating onto steel structures for corrosion protection, or there's some more obscure applications, which is spraying zinc onto concrete to protect the rebar. LPG gas cylinders widely have a zinc coating as the base level beneath the paint. Various oil and gas structures, wind turbines, the towers, the large towers that you see, especially the offshore, tend to be zinc or zinc aluminium, and a range of other applications. It's a very large encompassing industry for us, but these are just a few of the larger using areas, including the ships and vessels for the process. So again, a few pictures, some big surface areas on ships and vessels, just as a base coat below paint, pipework and process equipment, large fabrications which can't fit into a galvanizing bath, or if you're not close to a galvanizing bath, as well as small fabrications. LPG cylinders being sprayed in a facility, ductile iron pipe, structures such as playgrounds, just for a very good long-term corrosion protection, sculptures, wind towers, and the rebar protection on concrete structures are just shown there. So there's a short video here, which is just going to run. I'll talk you through some of the applications. It's just giving you a wide vision of the kind of things that are being done with our systems globally. So you'll just hop through the title screen. The first item that we'll see is an automated spray facility using arc spray. So these are sections for a new design of wind tower. So we've got two arc spray systems which are applying a zinc coating onto a pre-blasted piece of steel there. We go to a manual flame spray system here. This is an offshore structure. So there's a lot of similarities to the paint spraying that we'll cover shortly as well. The wire that you can see coming out the back of the pistol is the coating material. So that's what's creating the coating. Arc spray on a wind tower. So on a lot of wind towers, at the absolute minimum, the flanges and the internal weld areas are zinc sprayed, if not full structure. Ships and vessels, there's the massive industry for metallisation, and different parts of the world adopt it more strongly than others. This is one of our UK customers, again, spraying with an arc spray system in a scaffolded and sheeted up unit. This one is on new build boats. On oil and gas refineries, so this is flame spray, applying coatings onto pipes. Bit of a novel one for marine fabrication. So this is showing Metallisation's extension deflector as well. So what we're doing there is bending the flame so that we can get to the underside of those flanges, but that's applying zinc into those areas. And then general structural steel, again, flame spray being shown here, just showing that it's applied in a similar way to paint. Or some similarities, I should say. So the material selection for anti-corrosion, we're going to concentrate on the zinc today. So this has been touched on already by Martin. It's acting sacrificially with ferrous substrates. It forms an oxide layer, so it gives you a barrier coating as well as a galvanic protection. It's a predictable life under known localized environmental conditions. Typical pH range 6 to 12.5, and it's used in a wide range of atmospheric and immersed environments, ambient temperatures. Other alloys can be used in marine environments and for certain industries such as zinc aluminium as examples. A bit of information on coating selection. This is taken from the British Standard 14713. So you can see that the territory that we're in is long-term corrosion protection. So it's showing the hot dip galvanizing, which tends to be thinner film. But then we get up to hot dip galvanizing 150 microns versus sealed sprayed zinc. To get the 150 microns of galvanized, there's certain things that you have to do with the process. So it's not just your standard dipping process as Martin described earlier. And then going above it, 250 microns of sealed sprayed zinc. The sealer coatings will cover it shortly to give us the very long life of corrosion protection as seen here. There's a few salt spray comparisons here. So on the left, generally you've got paint coating, so you can see where you've done the scratch test. You can see rust is forming. The two central ones is a zinc aluminium and zinc coated samples, all after 1,000 hours salt spray. And then on the side, we've got a galvanized sample plate, as well as some duplex coatings using zinc and paint coatings on top. So you can see the difference in the metal sprayed coatings compared to just the paint coatings. And this is the big benefit that this brings to various industries globally. So let's have a look at a comparison to galvanizing. Benefits of metal spraying. The process isn't limited to pure zinc. So you can choose a material subject to the application in relation to the environment. That means you can spray zinc al, which is very good in marine environments as an example. It's got very low heat input. So unlike with galvanizing where you can potentially get thermal distortion, you don't get that distortion with metal spray because it's a very controlled process with very low heat input into the substrate material. Coating thicknesses can be locally varied. So on a structure, if you have more corrosion at the base, you can apply a thicker coating to the base and a thinner coating at the top, rather than with galvanizing, which is a uniform thickness all over. There's no limit to the size of fabrication that you can spray. And the fabrications can be sprayed on site. So instead of having to move something to a galvanizing bath, it can be done in your own yard. It can be done in your own spray shop, potentially. Metal spraying can be used to repair damaged sections of galvanizing. Again, it was touched on by Mike with regards to the paint. The same with the thermal spraying. Thermal spray zinc is the most comparable galvanizing repair because it is a pure zinc coating. So preparing the damaged area of the galv, grip blasting it, and then applying the zinc will give you equivalent corrosion protection, if not better if needed. It's proven to provide better protection than galvanizing. And when you have a fabrication with sealed hollow sections, with galvanizing you have to drill holes. With the metal spray process, you don't need to do that. So you can leave a structure completely intact without the consideration for drilling holes to allow the galvanizing process zinc to run in and out. Now onto the comparison with painting. So the benefits of metal spray. We've got no drying time, we've got no curing time. You grip blast, you metal spray, you spray the zinc, and instantly you have a coating, which you can measure, and you can then move to the next stage of the process. There's no dwell time, you don't need to leave it standing round. It's as instantaneous as that. It can be applied in a wider climatic range of conditions compared to painting as well, as far as temperature and humidity. Sprayed metals are more robust than paint, and again, Martin touched on this with regards to the durability, and even if it gets damaged, it still continues to protect. Corrosion protection continues even when the coating is damaged. As just touched about, it will create repair to the damaged area of the zinc as well. Sprayed coatings maintain a level of friction grip throughout the life of the coating. What this means is that if after so many years you have to go back and freshen up the aesthetic paint coating, there will still be a friction grip underneath, which the paint can adhere to. And the adhesion to steel work is typically better than paint spraying as well. Sprayed metals are often specified as base layers for painting due to the better adhesion. And properly sprayed and sealed coatings do not actually require painting other than for aesthetic purposes, because the corrosion protection is covered by the thermal spray zinc. So how do you thermal spray? Surface preparation is key. 90% of failed sprayed coatings are due to poor preparation. If you cut corners on your grip blasting, then with it being a mechanical bond, that can create a failure because you don't get the adhesion that you desire. Grip blasting is commonly used, not shot blasting, typically garnet on site, chilled iron or steel grit in-house. The whole purpose of this is to remove surface imperfections, rust, scale, etc., to provide a clean angular surface profile for the coating to adhere to, and to increase the surface area and provide a mechanical key for the thermal spray coating. The required profile, again, relating to EN 8501-1, we're looking for a grade SA3, SA2.5 at a minimum of cleanliness, with a profile not exceeding 100 to 125 microns. The other thing to consider is the form of the structure. So if you've got sharp edges, blast welds, you want to concentrate on those areas. So break the edges just so you haven't got stress risers. Give good blasting onto the weld areas, which are notoriously the most difficult to get the profile on. So applying the thermal spray coating, I'm just going to have a quick drink, if that's all right, guys. Many of the paint spraying principles apply to the thermal spray process. So you apply the coating within 4 hours of grip blasting and before oxidization of the profile. Any oxidization of the blast profile can affect the adhesion of the coating, in the same way with paint coatings. Thermal spray zinc coating is applied in multiple crossing passes with a standoff pistol distance between 100 and 200 millimeters. It's one of the key aspects of metal spraying and thermal spray is the spray distance, because the further away you get, the cooler the particles are and the less adhesion you get and the more dust you generate if you're not doing it correctly. Each pass overlaps the previous pass in order to achieve an even coating thickness as much as possible. You want to try to maintain perpendicular to the surface and no more than 45-degree angle of the pistol to the substrate. This gives the best coating properties. And typically crosshatch is used within the industry because it helps to give a nice even coating when you finalise a coating system. You apply the multiple passes and you continue to apply it until you've got the required thermal spray zinc coating thickness. Again, as soon as you've sprayed it, you can check this with positesters and alcometers. So the process is to apply zinc, flame spray. What we do, we have either oxygen acetylene or oxygen propane. We create a flame on the front of the pistol. We bring the coating wire through into the flame. The flame will melt the wire. Compressed air will atomize and create the molten particles, and this is then propelled onto the substrate material. You can see on this illustration here, the arrowhead here is the coating wire, and you can see, hopefully you can see just the little molten particles coming off the front end, which have been atomized off the front end of the molten wire. So equipment options, flame spray. Advantages, it's a handheld pistol. It's got a higher deposit efficiency compared to an arc spray system, and it's really flexible for site working where no electricity is available. Some disadvantages, there's a little bit more skill to it than arc spray. There's a startup technique and a shutdown technique, but very easily taught. Typically, it requires a higher standard of preparation compared to arc spray. We'd be looking to aim more towards the SA3 ideally. It uses combustible gases, and also there's gas changeover time as those gas bottles empty. For some coatings, there's a lower bond strength. Zinc isn't one of those coatings. It's relatively standard bond strength for flame spray or arc spray for zinc. And there's a bit more maintenance for flame spray compared to the arc spray because of soft seals and items like that within the pistol. So onto the arc spray process, we bring two wires together. One we apply, this is the electrical system, one we apply a positive charge and one we apply a negative charge. And we bring those two wires together at the front of the pistol. They're driven together and when they touch, it creates an electrical arc which melts the wire. And then the compressed air, again, atomizes it and propels it onto the substrate. For zinc, you get this lovely blue hue on the front of the pistol. So the advantages of arc, we can achieve higher spray rates subject to the amperage of the system, so considerably higher spray rates than the flame spray systems. It's simple to use. Generally, it's press a button, start spraying, pull the trigger, start spraying, finger off the trigger, push a button, and you've turned it off. When you compare coating costs, it's lower running costs for the coating, and with the electrical drive, it's a very reliable system. Disadvantages: arc spray systems are more expensive than flame spray systems, so that can be a consideration when people are investing in this equipment. You do require three-phase electricity on site where you're spraying. You have a lower deposition efficiency, and couple that with the higher spray rates, it can mean that it's a much dustier process. But this can all be managed with extraction and filtration. So as much as that's a negative, there's a lot of advantages which make the arc a standout system for things like spraying big, large flat areas such as ships and vessels. So it's a cold process. This is just demonstrating it. So we're actually going to spray metal here onto business cards and onto paper. If he stopped and just pointed it straight at the paper, yes, it would set on fire. But you can see that we're actually applying the zinc or metallic coating onto materials that are combustible. So it just shows that it can be controlled, and it's a cold process in its own right. So as far as testing goes, thickness can be checked with eddy current DFT gauges such as positesters, alcometers, the same as what you'd use for dry film paint tests. If you're spraying onto stainless substrates, thickness can be checked with witness plates, but there's also some equipment that will read on stainless steel substrates as well, so you can get some readings. As far as adhesion goes, this is quite accurate. It's a destructive test though, so it's pull tests using dollies on witness plates. Can be done on the job, but with care, but generally this is done on a plate which is sprayed at the same time. We use bend tests on witness plates, so this is where we spray a steel plate and we'll bend it over a mandrel, and what that will do, you're looking for the coating to bend with the plate so that it just shows that you've got good adhesion and good cohesion within the coating. And rarely we have scratch tests, but in the industry, that's probably not one that's used very widely. So for sealing, sealers, many coatings will benefit from being sealed, but they're not always essential. So if you've got a very thick coating, generally the likeliness of through porosity throughout the coating, you get micro porosity within the coating, but the chances of that being through porosity is minimized or removed. For thinner coatings, 100 microns up to 250 microns, generally you'd use a sealer coating. So our sealer coating is a low viscosity material. It's like a thin down paint. It's applied onto the thermal spray coating. The porosity in the coating isn't like a paint bubble, it's micro porosity. So when you apply the very thin sealer onto the surface, it sucks into the coating like a sponge and it seals off all of that porosity. So what that does is it enhances the life expectancy of the coating because it removes the through porosity, and it reduces the exposed surface area. And you can have coloured sealers as well, so it can offer a more desirable coloured appearance to the coating itself. Sealers also smooth the spray surface, so it means that they can be kept cleaner for longer. The standard appearance of a spray coating is very much like a light blasted surface finish. So when you put a sealer coat on there, it does give you a smooth finish to it as well. The sealer coat should, for thermal spray zinc coatings which are going to be sealed, you should be sealing it within 24 hours of application of the thermal spray zinc, and this is to avoid oxidization. I think Michael discussed this as well with regards to the zinc oxide forming on the surface can create problems with sealing it correctly otherwise. So finished metal spray coatings, duplex coating systems. This is generally layers of metal spray, sealer and paints which are specified for given applications. The duplex coating is stronger than the sum of its parts, so the paint will add an extra layer of barrier protection to the zinc, while the zinc protects the paint from underfilm corrosion and scratches and holes. An example of a coating specification in the UK is the UK Network Rail N1 specification. This is used for infrastructure and bridges. So it's a grit blast substrate to SA3, thermal spray zinc or thermal spray aluminium for 100 to 150 microns, epoxy sealer to a maximum of 25 microns dry film thickness, and then a primer and a top coat. And that's used on pretty much all of the infrastructure for Network Rail in the UK for the rail network. Finally, just a bit of information about the considerations. If you're going down this route, a bit of thought into the structure and the design can help, because what this enables you to do is to consider the weld areas, consider the areas that you need to access with the coatings. So in some instances, you can design features so that you can get to all of the areas to do a complete coating system. And then sharp corners and edges, again, just filing the edges and the corners just so that you've got rounded edges so you don't create any potential coating issues. And again, all of this is covered by British standards to give you some design considerations for thermal spray in the standards shown here. So I'd like to thank you for your time. It's been a bit less application and a bit more process on how to do it, with it being a niche industry and a deep niche application. But yeah, we're open to any questions, and just wanted to say thank you for your time today.
Thank you so much, Ian. I found it very interesting to learn all the applications for zinc thermal spray, particularly seeing how it's done in all those videos. So again, if anyone would like to be in touch with any of our speakers, please be sure to leave your details in the chat and we can respond to you after the session. We're going to move now to the Q&A. I see we do have a couple of questions. And I think Mike did answer some, but I think I'm going to ask them anyway, just so that the rest of the audience can hear what those answers are. So actually, these are for Michael. So I'm going to pass this to you, Mike, and it says, is a zinc paint coating enough to save cost to protect the hull of a boat, or would you recommend additional anodes or an ICCP system to be fitted? If you'd like to answer that one. Okay,
generally, we don't specify zinc coatings for the full immersion. Non-zinc systems are generally used on these as barrier coatings with anodes attached. So I think one of the reasons that anodes can easily be replaced, whereas a zinc coating, once, shall we say, it's used up, is harder to replace. So that in my experience, is generally a non-zinc for the ship's hulls.
Is there anyone else who'd like to give an extra input on that? No. All right. I'm going to move to the next question. This is also from Jacques de Klerk. He also sent this question, and he said, would you also recommend a component be hot dip galvanized, or will the zinc coating be enough protection in a marine environment? Michael, we'll take an answer from you, and then we'll move on to Martin, because he also gave an answer there.
Yeah, it does depend on, obviously, on environment. There's also factors such as the cost and the structure sizes, for example, whether you can actually galvanize a structure or not. But zinc paint coatings on their own can offer excellent durability. But you, as Martin has mentioned in his answer below, I think you can also apply the paint coatings over galvanized systems, the duplex system, and get a very good system with that as well. You have to prepare the galvanizing correctly, of course, to get the adhesion between the galvanizing and the paint, but it usually comes down to cost factors and sometimes clients' choice as well.
Martin?
Yes, if you remember well, in the durability curve that I showed in my presentation, you can see that in severe aggressive environments like C5 and CX, where chlorides are very important for corrosion, you see that the lifetime of zinc coatings goes down as well. And to give it an additional protection, you can apply a duplex coating. It is generally known that the durability of duplex coating is longer than the sum of the individual coatings. That has been investigated by a researcher called Van Einsbergen. So there's an enhancing effect of applying coating on top of zinc coatings. We do see that the zinc protects the paint. The paint protects the zinc, and the zinc supports the paint in terms of adhesion. In terms of immersed conditions, it's generally not used at the moment, but we do see that some producers from zinc wire for the thermal spray process has done extensive immersed tests with duplex systems on corrosion test site at Helgoland. And there it's seen that specific duplex systems made out of metallized coatings of zinc aluminum 15% with a paint coating on top would stand out for a very long time in immersed conditions, longer than 10 years time before some degradation can be seen on the surface. This is still in the experimental phase, but we would like to promote this, of course, under the users of corrosion protection systems for immersed conditions. If anyone wants to hear more about it, you can contact us.
Thanks very much, Martin. We do also have a message from Charles Hubert, and he has raised his hand. I am able to allow people to speak. Martin, should I allow Charles to talk, and then he can ask his question live?
Yeah, sure, why not?
Okay. Charles, I'm going to allow you to speak. All right, you're live. You can go ahead, Charles.
Yeah, I'm just unmuting. Hi, everybody. Charles Joubert from Zinc Epoxy Pty Limited, based in Johannesburg. Just to respond to some of those questions on saltwater immersion, it is definitely possible. We've done quite a bit of work on our zinc coating for saltwater immersion. I mean, we've just been accredited with IM4 4,200 hour CX splash tidal zone through all-weather laboratories in London, and with zero degradation. So that incorporated pull-off tests, that also incorporated cathodic disbondment testing, which was all passed. So it is definitely possible to have zinc coatings that can give you very good longevity immersed in sea conditions. And I agree with one of the speakers that if you do apply a polyurethane top coat, you can double the longevity of zinc-based coatings. What's quite critical with the zinc-based coatings is we've done extensive work on creating a totally hydrophobic zinc-based coating from surface of the coating to top of the steel substrate. We found that to be the best possible solution in immersion environments.
It's interesting that you mentioned that, because there's some recent research that came out that shows that zinc oxide can add to the hydrophobic properties of top coats to reduce the water penetration or the moisture penetration in the organic coatings.
Absolutely, and the more hydrophobic the system is, I mean, we also use a filler which is quite unique in conjunction with the zinc. Our zinc systems are 85%, so we are on the upper spectrum of the zinc coatings, as you showed earlier in your presentation. So the other critical aspect of a zinc coating is obviously adhesion and bond between either an epoxy or a polyurethane top coat. Standalone pull-off tests with a Positector hydraulic puller, the 20 diameter dolly, is anything up to 21 MPa on the zinc coating alone, or 21 MPa with the polyurethane or epoxy top coats on top of the zinc coating. So adhesion is also a critical factor.
Yeah, I don't agree with that. Adhesion is with any coating system is critical.
Absolutely.
It's the pull-off. pull-off testing, you can definitely get good pull-off results. I think one of the things, as I mentioned in my presentation, is you have to control the film thickness of the zinc coating, because they can be cohesively a bit weaker than a non-zinc coating. And that's where we sometimes see issues where there's over-application of the zinc, and then you get a break in the actual coating itself. The adhesion to the substrate's okay, but you get a break within the zinc cohesively.
Yeah,
So Michael, you mentioned that there can be issues with the adhesion of top coats on zinc silicates. I was wondering, can it help to apply a conversion coating on top of the zinc silicate coating, like a phosphate, for example, to improve or increase the adhesion of further top coats?
The adhesion between the adhesion between the coats is generally okay. With the zinc silicate, for example, you do. My personal preference is to use a specific sealer coat, a similar way on the metal spray as well, really thin down coating, so that you can tell you put a sealer on, for one thing. You can use the mist coat, full coat, but generally if you do that well, you get good adhesion between the coats. But if you over apply the zinc coating, be it epoxy or certainly zinc silicate, then you can get a break within the actual zinc coating itself, a cohesive break. And that's where we sometimes see, we call them adhesion failures, really cohesion failures more than anything else.
Yeah, Michael, I agree with that statement. And that's why we've done extensive work. So we achieve, as I said earlier, with up to 200 micron thick zinc coatings, 21 MPa pull-offs without cohesion failure. And then applying either a polyurethane or epoxy top coat onto our 200 micron zinc coating, and we're still achieving 21 MPa pull-offs. So it's quite remarkable.
Yeah, that's good. That's good. I think one of the drawbacks maybe with zinc coatings is obviously the cost as well, and that's where we see some customers who don't use them for that reason, because of the extra cost compared to a non-zinc system. But they do miss out, I think, on some of the performance. But it's always a cost-benefit equation, isn't it, in these cases?
Always, So and I tend to agree with you there, because then you can balance the thickness of the zinc coating with a 50 or 100 micron top coat. So yeah, I agree with you. Cost is always especially in these economic times, is always a factor.
I do see another raised hand, Shannon, from Keith.
Yes, from Keith Mackey. I'm going to allow him to speak as well. Oh, it's gone. Yep. Keith, if you can put your hand back up, then I can allow you to speak as well. Charles, thank you for your input. I'm going to put you on mute.
Thank you.
Right, Keith, you are live. You can speak.
Right, can you hear me now?
Yes, we can.
I followed this discussion we've just had with great interest. I spent most of my working life in the fishing harbours, where we developed a standard system for all our steel work. It was sandblast, inorganic zinc silicate. I think it was about 70 microns. We wanted to keep the thickness not too thick to avoid the mud cracking problem. And then we used a polyvinyl butyryl seal coat, about 10 microns or less. It had to be kept very thin. And once we put that seal coat on, we had no more problems. And we had our standard top coat was an MIO alkyd, a standard paint for galvanized corrugated iron roofing. That was the build coat, and then a alkyd enamel color coat to finish it off. And we had fantastic service out of it. 15, 20 years. It hardened up very nicely. Sticking it on slipways, there's a lot of mechanical damage on that sort of thing. We never bothered to go to the epoxies, silica, urethanes, and that sort of stuff. The only thing that worried me, which I never got around to solving, was my fear that if we use it for steel immersed in the seawater, we would get delamination. And I never got around to solving that one. Thanks.
Okay, thanks, Keith. I think that I'm a little bit surprised with the system. Obviously, you've had good performance with it, but as a general rule, we wouldn't normally recommend using alkyd coatings over zinc maybe the silicate in your case has helped there, but that's because the zinc can saponify the alkyd in damp environments, so it becomes a bit soapy, and you get adhesion losses. So
I agree with you, Michael. When we first tried it without the sealer, we did get delamination with this saponification. But that the polyvinyl butyrol did a marvelous job of just solving that problem.
Yeah, that sounds like you had good success with that. So I think the key thing certainly with the zinc sealer is getting the right sealer and getting it applied in the right way. You find sometimes on large jobs where zinc silicates are used that 95% of it is okay, but you'll get one area where you get this pinholing effect if the sealer's not been applied correctly, or the zinc silicate's not been applied correctly. Maybe it's applied a bit dry and you get a more porous area. But if you do it well, you do get very good performance. But it's not as easy to apply as a zinc epoxy, but it does give good performance if you do it right.
So Keith, to add on that, I think it's maybe interesting to know that zinc-rich paints do perform very well on ships, on fishing trawlers, for example. But I do know of a couple of examples in Scandinavia or in Alaska where people have metallized their ships instead of applying a zinc-rich paint with a top coat on top of that, and that seems to perform very good as well. If the ship goes back to a dry dock after 5 years, for the mandatory inspection, they only need to clean or water blast the top coat. You don't touch the zinc coat underneath, but you can very mildly remove the bad painting parts, apply a new painting on top, and your ship is ready to go for another 5 years.
Okay, thanks very much, Keith and Martin, for that input. Charles has got his hand up again. I'm just going to allow him to speak, and then we'll take this last question.
Can you hear me?
Yes, we can.
Yeah, just to Keith, just to answer your question on mud cracking, our system can be applied up to 300 micron one shot, zero mud cracking. If that answers your question, Keith.
Keith, if you'd like to have any comeback there. Just need to unmute. No, he seems to have left the chat. So I think thank you very much, Charles, for that input.
Thank you.
I think then that's all the questions we've got for now. If anybody has not had a chance to ask their questions, please do send us an email afterwards. We will be able to be in touch with you after that. And I think now we have reached the end of our webinar. So I would just like to thank everyone who participated in the live Q&A, and thank you also for your input if you did speak up. As I said, if we didn't get a chance to answer you, we'll happily connect with you after the webinar. And I think that will bring us to the end of our session. I'd like to take this opportunity to say thank you to our panelists, Martin van Leeuwen from the IZA in Belgium, Mike Taylor from PPG Protective Coatings UK, and Ian Blacklock from Metallisation UK. A special thanks also to Kevin Watson from the South African Institute of Marine Engineers and Naval Architects for arranging the CPD points. Thank you to our attendees for taking the time to join us for this specialist workshop on zinc anti-corrosion coatings. If you would like more information, please be sure to visit the International Zinc Association's website at zinc.org. I'll just give that to you again. It's www.africa.zinc.org. So just before I end things off, I'd just like to pass on to any of our panelists, if there's any last words you'd like to say.
Well, let me start, Shannon. I would like to thank Creamer Media for organizing this webinar. It's important that we spread the word on the good performance issues of zinc coatings to protect our valuable steel assets. And these kind of webinars are very helpful to do that. Especially in the pandemic times, we have learned that we can still gather together and exchange ideas and information. So thank you for the organization, and this has been a very interesting webinar.
I'd just like to say thank you for inviting us to present at this webinar as well, and thank you for everybody's time.
Yeah, and I would second that. Thank you very much for the opportunity, and thanks, Shannon, for the organisation. And if you've got any questions, you know where to find us. So.
Thank you very much to everybody. I really appreciate your time. And the recording of today's webinar will be sent to you in due course. If you have any additional questions, please do be in touch. You can reach us at shannon@creamermedia.co.za. Thank you very much. Stay safe and stay well, and goodbye.